Your exponent and your base. Your exponent tells you how many are being multiplied, and the base is the number being multiplied. Okay, so 3 to the 5th is 3 times 3 times 3 times 3 times 3. And if we're going to evaluate that, I'm going to do 5 3s to give us 243. An exponent of 1, I mean, it's literally saying you have 1 5, so it's the same thing just as 5 or any number. All right, so if we were to evaluate 6 squared, 2 6s, so 6 times 6, 36. 5 to the 3rd is 3 5s. So it's 5 times 5, which is 25, times 5 is 125. And 2 to the 4th is 4 2s. So 2 times 2 is 4, times 2 is 8, times 2 is 16. Oops, that's not what I meant. We have powers of 10, and that is 10 raised to a power. And that gives us a 1 followed by however number of zeros are on our exponent. So if I say 10 squared, that's 10 times 10, that's 100, right? 2 zeros squared. So I can easily say 10 to the 8th. I just write 8 zeros. So you don't actually, when you have 10s as your base, you don't actually have to multiply out that many 10s. You just take your exponent and count that many zeros. So 10s are a nice little, that gives you a nice little shortcut. Much in the same way multiplication and division are opposite of each other, or addition and subtraction are opposite of each other, you have exponents and roots. Now a square root is basically, when you have roots, a square root, we don't put a number on it, but it's essentially the same thing as that with a little 2. And so if you have 3 squared is 9, to undo that, you take the square root of 9. So square roots undo exponents of 2. So there's a couple ways that we can look at this. I'll give you a list. Did I leave space? Yes, I did. Okay. I'll give you a list of all the perfect squares up to 100, or up to 25. And then you can look at that list and go backwards, or we can do factoring. So let's skip to the list.
What about when the numbers are not perfect squares?
We'll go over that later. For right now, though, we're going to be just dealing with perfect ones. Okay, 1 squared, that one's easy. 1 times 1. These are the ones I always forget. By the way, did you guys know you could give yourself a scientific calculator on your computer? So when you pull up your calculator on your computer, it normally looks like that, right?
Mm-hmm.
If you go to View and you click Scientific, you now have a scientific calculator.
Does that have the negative numbers on that?
Uh-huh. So I can do squared. Okay, now when you have 30s, 40s, 50s, this is like 3 squared with a 10 squared. So you get 900, 1600, 2500, etc. So you double the number of zeros. Square the first number and then double the number of zeros. I'm not recording. Okay, so we can make a factor tree if you don't have your squares memorized. What I can do is I can look at 64 and I can say, okay, well that's even. So it'll divide by 2. So it's 2 times 32. And then I can say, okay, 32 is even. That's 2 times 16. That's 2 times 8, 2 times 4, and 2 times 2. Okay, that's a factor tree. So you just keep splitting it until you have nothing else that you can split.
So what is the answer?
Well, every pair of matching numbers is a square, right? Because a square is a number times itself. So every pair you have that matches,
It's 2.1?
you're going to circle them. So I have 3 2s that match, 3 sets of 2s. So my answer is then going to be 2 times 2 times 2. You take out 1 for each matching pair. So if you didn't know that the square root of 64 was 8, you can figure it out by splitting it all up, and then for each matching pair, you write down 1 and multiply them back together.
Hold that up for a second.
I will.
So on that test and stuff, are you allowed to use
If you have a big number like this, so 1764, hey, that's even. I can divide it by 2. 882, which is even, so I can divide it by 2. Okay, 441, not even. But if I add this together, I get 4 plus 4 plus 1, which is 9. Did I talk to you guys about that?
No.
If you add the digits of a number together, so if I do 4 plus 4 plus 1, that equals 9. 9 divides by 3. So this will divide by 3. Not because it's 3 numbers, but because the sum of the digits divide by 3.
I see what you're saying.
So if I do that, that's 147.
The Chinese lady was talking about that.
And if I add these together, I get 1 plus 4 plus 7, which is 12, which will divide by 3. And then 49 is 7 times 7. And now I have a pair of 2s. I have a pair of 3s. And I have a pair of 7s. So my answer to this is going to be 2 times 3 times 7, which is 6 times 7. So 42 is the square root of 1764.
What about if you don't have a pair?
Not division, but divisibility. Ways to tell if a number will divide by certain numbers or not. Okay, so to check if it divides by 2, it's going to be even, so it's going to end in 0, 2, 4, 6, or 8. If it ends in those numbers, it'll divide by 2 evenly. No problem. For 3, you add up the digits. So whatever digits are in the number, you add those up, and if that divides by 3, then the original number divides by 3. So, for example, if I have 723, okay, 7 plus 2 plus 3 is 12. 12 divides by 3 evenly. So 723 will divide by 3 evenly, and it's 241. Oops. Okay, so it's just a way to quickly tell if a number will divide by 3 or not. For 4, if the last 2 digits divide by 4, then the whole number divides by 4. So if I have 4,328, okay, I'm going to look at these two right here. Well, 28 does divide by 4. So 4,328 will also divide evenly by 4. Okay, 5 is another really nice one. To know if something divides by 5 or not, it has to end in 0 or 5. For 6, if it's even, and you can add up the digits and they divide by 3, it'll divide by 6, because 6 is 2 and 3 together, so if it'll divide by both 2 and 3, it'll divide by 6. Usually though, if you're talking about factorization, you want to stick with your prime numbers. 2, 3, 5. First, you're going to perform all the operations inside parentheses or other grouping symbols, and by other grouping symbols, that's brackets, braces, fraction bars, absolute value. Then you do any expressions with an exponent or a square root. Then you do multiplication or division in the order they appear, moving across the problem from left to right, the same direction you read. And then the same with addition or subtraction in the order they appear. Now there's a way to remember this. Actually, there's a couple ways to remember this. Hold on, did I put it on the next page? Yeah, we'll do it on the next page. So, old school. Please excuse my dear Aunt Sally. Apparently Sally has some issues. She needs excusing. Parentheses, exponents, multiplication, division, addition, subtraction. Now remember though, you don't have to do the multiplication before the division. You do those in order that they show up. It's just that multiplication and division have to come before addition and subtraction. Okay, new school. PEMDAS. They made up a word, PEMDAS. Parentheses, exponents, multiplication, division, addition, subtraction. You do either one. When I was teaching middle school, I had my students make up one, and I'm going to have to change the color for this. They made up their own, and it was purple elephants, munch daisies, all Saturday. I like that one. I thought it was very clever. You can make up your own. Just something that'll help you to remember, like the order. Using our order of operations. Okay, first we have no parentheses. We're going to move left to right. We have division. Yeah. So what I usually do when we're working down a problem is I start writing exactly what's already there. 10 divided by 2 is 5. That's really not attractive. Okay. 10 divided by 2 is 5, right? And then I'm going to write everything else exactly the way it was.
Why do you have
A plus 3, sorry. Thank you. Plus 3. Okay, so 15 minus 5 is 10, plus 3, 13. You don't have to do it this way. I just think that when I'm putting it up on the board, it makes it easy to see what I did for each step. So, okay, here I do have parentheses. So 5 minus 2 is 3. I write down everything else exactly as it was. 3 times 7 comes next. That's 21 minus 1 is 20. Now here I have a radical. This radical is actually counting as two things. It's counting as a grouping symbol and as an exponent. That's
So,
because see how it's grouping this 64 and 36 together? So you need to do that first.
and then you use the square root of that number, so.
Uh-huh.
You add the numbers and get
You have to, yeah, you have to add before you take the square root of them. So 64 plus 36 is 100. The square root of 100 is 10. Okay.
So minus.
I'm going to leave this right here for just a second because I want to come down here and do kind of like a little notation. There's a difference between this and this. Okay? The difference is this is negative 2 times 2 times 2.
It's a complete value, right?
And the negative hangs out outside. This is negative 2 times negative 2 times negative 2. Okay, here's where I get weird on you. Exponents are like a taser, a handheld taser. It's only affecting the one thing it's directly touching, right? So if I were to, go insane and have a taser and come running over here and taser you, it's not gonna shock her, right? Because I'm only touching you. Now, let's put you in a parentheses and you're holding hands or something and I taser, then you're touching each other. So what's happening is right here, the exponent is only affecting the 2. Here, the exponent is affecting the parentheses, which means it's affecting everything inside. No, the first one, this negative isn't being touched by this, so the negative just hangs out front.
Okay, I see what you're saying about affecting everything.
And in this example, because it's a third, it won't make a difference. I'm still going to get the same answer. So 2 times 2 times 2 is 8, and that negative is out there. Well, negative 2 times negative 2 times negative 2 is also negative 8. But if I was squaring, it would make a difference. 2 squared is 4 with a negative out front, whereas negative 2 squared is negative 2 times negative 2, so that's positive 4. So it does make a difference. So that's why I wanted to point it out, just to make sure you understand. So this negative right here, or this minus, it's not being cubed. And like I said, it won't make a difference on this particular example. We'll get the same answer, but
So that's a negative 2, it's not minus 2
Well,
to the third?
it's minus, yeah, it is, it's
Oh,
minus
okay.
2 to the third. But I want to make sure that you catch the difference. So this is going to be 10 minus 8, which is going to give me a 2. Nice, pretty straight line.
How would that work if it's like multiple numbers inside the parentheses with 3 on the outside?
Well, you would do, let's say you have like 4 minus 6 squared.
Yeah.
You're going to take the 4 minus the 6 first because it's in the parentheses. And then you're going to square the negative 2, so it's negative 2 times negative 2, so that's when you get a positive 4.
Okay.
Okay.
So negative times negative
Is a
equals
positive, yeah. Okay, so they're called nested. You know, you've heard of nesting tables or nesting chairs. They stack inside each other. Have you guys heard of those? Nesting dolls, things that, yeah.
Can you spell it?
It's right here, nested. It's things inside of each other that fit inside. So what you do is you start inside and then you work your way out. So we're going to do this 5 plus 2. And everything else gets written exactly as it already is. Okay? The only thing I changed was this 5 plus 2. Here. Actually, hold on one second. Together. So now I'm inside these brackets. Inside the brackets, the next thing I need to do is the exponent, because exponents come before addition. So 7 squared is 49. Okay. Now I have addition still inside these brackets, so that's what I'm going to do next. So I'm going to get 53. Okay. Now, I kept the brackets there because this 4 was right next to them. And if there's nothing in between a number and a parenthesis or a bracket or anything, it's multiplication. So I kept the brackets in there to indicate it's still multiplication. So I have -4 or 4 times 53. Well, that's going to be 212. And everything else is going to stay the same. Okay. Now I'm down to braces. And I have addition and subtraction inside the braces. So I can do all of this. 300 minus 212 is 88 plus 8, 96, minus 31, and that's going to give me 65. Okay. Sorry it got all squished at the bottom there. So you take it one part at a time. Big long problems like this, I know for some, visually that's overwhelming because there's a lot going on. So you just look at one little piece at a time, step by step by step, and everything else just gets copied down. Algebra, invented by Sir Isaac Newton. Blame him, not me. Okay. Variables, they're used to represent quantities that are subject to change. That's why they're called variables, because the word variable means changing. And constants are numbers. If I tell you 5, it's never anything other than a 5. So that's why those are called constants. And then together they make algebraic expressions. Yeah, they can change. So x today might be 3, x tomorrow might be 75. It just symbolizes unknown. Any letter just symbolizes an unknown. Now, a constant is a number. So,
The other one are letters.
yeah, so variables are letters or other symbols, but usually it's letters, and then constants are numbers. And they're numbers by themselves. Okay, so like if I have 2, that's a constant, but 2x is not a constant because it's attached to an x. Does that make sense? So, not constant. Actually, while we're on it, I might as well go ahead and give you this word too. Coefficient is a number attached to a variable. So if I say 2x, the coefficient is 2. All right, so how do we do this? We're going to evaluate an expression for given values of a variable. Wow. All right, so I have 5a plus b, and then they say for a equals 6 and b equals 10. They're telling us what a and b equal. So what we're going to actually do is we're going to take this 6 and replace a with it. And we're going to take this 10 and replace b with it. So instead of being 5a plus b, we're going to have 5 times 6 plus 10. So that's going to give me 30 plus 10. So it's going to give me 40. Now you'll notice I'm not putting any equal signs here. The reason I'm doing that is because this is an expression. An expression has no equal signs. Once you add an equal sign to it and it becomes, it's, you know, like 5a plus b equals something, it becomes an equation, which is a different kind of scenario. So that's why I didn't put any equals here. X is 12, Y is 9, Z is 4. So what I'm going to have is 12 minus 9 plus 4 squared. So that'll be 3 plus 4 squared, which gives me 7 squared, which gives me 49. Okay, so multi-step application problems. We've got a car that's $18,340. You're paying a $2,500 down payment, and then you're paying the rest in equal monthly payments over a 4-year period. We're pretending there's no interest.
Thank you.
Wouldn't that be nice?
No, nice.
Okay, so to figure out this problem, first we need to see how much does he still owe after the down payment. So we take that $18,340 and we subtract our down payment. And he still owes $15,840 owed still. Okay. And now he's paying it over a 4-year period. So how many? 12 months, 4 years, so there's 48 payments.
Divide that by 3.
So I'm going to do 48 into 158, 40? Well, 48 does not go into 15. Okay. Determine how many times 48 will go into 158. The easiest way to do it is I'm going to look at 4 and 15. 4 goes into 15 3 times. So I'm going to try 3. 144. Subtract that. Bring down my 4. Oh, hey, look at that, 3. 144. Bring down my 0. It goes into 0 0 times. So his payments are $330 a month.
We're not that
Okay, so Linda is driving from Clayton to Oakley, and then from, or she can go from Clayton to Pierceland to Oakley. We're trying to figure out which is faster. Straight line's always shorter. It's not necessarily faster. So, because she's going to go, if she goes straight from Clayton to Oakley, she's going to have to travel on mountain roads at 40 miles per hour. If she goes Clayton to Pearson to Oakley, she can go 60. So what we want to do first is we're going to figure out what's the total distance between here. So that's 180 miles. So she'd be adding 60 extra miles.
That's 20 miles faster, right?
Not necessarily. So if we do Clayton to Oakley directly, she's going to go 120 miles at 40 miles per hour. It's going to take her 3 hours. Right? Does that make sense? If she goes Clayton to Pearson to Oakley, she's going to go 180 miles at 60 miles per hour. This is a terrible example. It's going to take her 3 hours.
Awesome.
That is an awful example.
The example is that she's driving faster. And
But she's going further.
Yeah.
So, but they're saying which route is taking less time. Well, neither.
Trick question.
Yeah, it's a trick question. So really, Judgment call. Do you want to drive really fast and put more miles on your car, or you want to drive slow and...
Also
Straight
depends
shot.
on gas tank of the car, which one. If it's the longer one, bigger chance of having off the gas tank.
that- Yeah, so, it just really, it depends.
The same amount of miles or whatever.
Same distance, or same time, different distance. So at that point, it's a judgment call. I would take the short trip.
Less gas.
Yes.
What about,
Depends on what type of scene.
The word mean is interchangeable with the word average. They mean the same thing. So an average is a mean and a mean is an average, and you take the sum of the values and you divide it by the number of the values. So let's say we want to do your average in your chemistry class, and your name is Ashley, everyone. You're all now Ashley. And you've taken 6 tests in chemistry, and we want to find your average score. Okay, so we take the sum of the values. And we divide that by the total number. Well, there's 6. So we divide that by 6. If you look at that, you're thinking, well, she's got all these 90s, but this 72 brought her way down.